Good morning. Pasensya na late. Fresh from the airport. 8:30 ako dumating. Sakto, 9:30. Anyway, the topic, as mentioned, is how to estimate site-specific wind loads. I decided to talk about this because while I was doing yung doctorate ko sa Japan, and well, after it, parang I was asked this question, how do we estimate site-specific wind loads? And I thought baka you might be interested in the answer, or my answer at least. But before that, I'd like to, siguro baka nabanggit na rin sa inyo, sorry, wala ako kahapon nga during the start of this seminar, but what is wind engineering? So usually, pag may kausap ako, and then I tell them, I studied wind engineering. Ang una nilang iniisip, itong mga, basically ang una nilang iniisip, wind energy. So mga wind turbines. Halimbawa, ito sa Northern Luzon. But, I mean, tama naman yun, partly, because wind engineering really has many subfields. Wind energy is one of them, but actually structural wind engineering is also one of them, as well as environmental wind engineering. So may structural, environmental, tsaka energy. Kung mapapansin nyo, if you're familiar with the 6 specialty divisions of civil engineering, so pumapasok din dyan yung structural engineering, tsaka environmental and energy engineering. So sa PICE, meron tayong 6 specialty divisions ng civil engineering. So you can just imagine na parang yung wind engineering, parang specialization or ng civil engineering. Or basically, it's a civil engineering study. That's why we're studying here. And more specifically, ako yung background ko is structural wind engineering. So, kumbaga, in a way, parang nung nag-masters ako, ang minasters ko noon, structural engineering. Tapos parang yun na nga yung doctorate, parang pinili ko, parang naging mas makitid pa yung pinag-aaralan ko. So anyway, parang subfield siya, subspecialization ng structural engineering. Of course, so maraming interested din in earthquake engineering, let's say vibration of structures, steel design, and so on. So maraming fields, of course, in structural engineering. Wind engineering is one of them. Yun. So may definitions of civil engineering. Ito, nakuha ko sa ASCE website, pero when I was an undergraduate, ito yung sinabi sa akin, or natatandaan ko ng definition of civil engineering. It is the art and science of using the resources of nature for the benefit of man. Ngayon, yung wind engineering, ito naman yung definition. It is the rational treatment of interactions between wind in the atmospheric boundary layer and man and his works on the surface of the earth. Ibig lang sabihin po niyan, yung may portion yung atmosphere, of course, na ito, kumbaga nararamdaman natin, na nararamdaman or nakaka-apekto ng mga building, etc. So, pinag-aaralan lang din natin yun. So, yun lang basically wind engineering. So, nabanggit ko mayroon ng 3 parts. I don't know kung naka-attend kayo in one of previous presentations sa ASEP or PICE. Introduce rin namin yung concept na typhoon engineering. So, syempre dito sa Philippines, typhoons ang concern natin. And when we say typhoons, of course, may wind, pero may flood din, may rain, and so on. Madaming structures na damage, and so on. So, actually, when we say typhoon engineering, ayun, marami ring fields yan, wind engineering, structural engineering, etc. In general, civil engineering is an important component of typhoon engineering. So anyway, yun lang, a very brief introduction sa wind engineering. And to answer yung topic, that question, how to estimate specific wind loads, I have 4 parts. Actually, if you've got a copy of the handouts I prepared, that's also the paper I presented at the PICE National Mid-Year Convention sa Subic noong June. So may 4 parts. Brief introduction, kumbaga I try to see bakit kaya naiisip ng ibang engineers ito, bakit sila interesado dito, and I have observed that many civil engineers, structural engineers are interested first in earthquake engineering. So I'll talk about, let's say, site-specific muna hazard assessment in the context of earthquake loading. And then, ipapasok natin yung sa wind loads and concluding remarks. And if we have time, I'll just answer some more common misconception, but really it's more information for you to learn. So, introduction. Are you, any of you familiar with these pictures? Do you know when this happened? Yeah. So, yeah, actually, well, tama. May part, at ito sa dagupan ito, Pangasinan ba? Nakalimutan ko na eh. But anyway, yung mga nagkaroon ng liquefaction, pero ito sa etong mga to sa Baguio, yung Hyatt, this is Baguio Summit Hotel. So 1990 Luzon earthquake. Interestingly, so madaming nangyari na, madaming namatay, madaming damage. Interestingly, pagkatapos mangyari yung earthquake na yun, 1991 nagkaroon ng unang ASEP earthquake design manual. 1992 na update yung NSCP, National Structural Code of the Philippines. So ganun tayo sa, well, I guess sa buhay, pati sa engineering. Pag may nangyari, doon tayo natututo. Kumbaga sa mga, well, you can say mistakes. But anyway, hindi lang naman yun eh. I mean, kahit nung, let's say, sa US, nagkaroon ng 1989 na earthquake sa San Francisco yan, 1994 sa LA, 1995 sa Japan, etc. Maraming earthquake. Of course, recently, sa Haiti, tsaka sa Japan. And then, kumbaga, kasabay nito, basta may earthquake na nangyari, nagkakaroon ng initiatives. For example, yun na nga, isang example ito, after the 1990 Luzon earthquake, pero let's say, karugtong niyan yung nag-umpisa yung DQRP program ng PICE tsaka ASEP, Disaster Quick Response Program. So ngayon naging EQRP na yan, Earthquake Quick Response Program. And then, likewise, nangyari 94 earthquakes sa LA, nagkaroon ng UBC, Uniform Building Code 1997, yun yung naging basis ng 2001 NSCP natin, nagkaroon ng, and then naging International Building Code, and then meron, medyo, I guess, baka napag-usapan na kahapon or pag-usapan mamaya, medyo mas sumisikat na sa mga civil engineers, structural engineers, yung performance-based seismic design na tinatawag. Basically, dun pumapasok. Sa performance-based seismic design, dun pumapasok yung kailangan ng gumawa site-specific analysis. Ngayon, if we look at individual disaster events in the Philippines, so ito, average number of people killed, injured, or made homeless, and average number of average cost of damages per typhoon, and then per earthquake, per flood. Makikita nyo, ang laki. I mean, malaki yung average na nakokos na damages and napapatay due to typhoons. Of course, larger pa rin yung earthquake. Mas maraming namamatay due to earthquakes and even due to volcano. But in terms of cost of damages, andyan yung typhoon and earthquake number 1, number 2. But basically, syempre, in general, mas takot tayo sa earthquakes. Basically dahil maraming namamatay, nasasaktan due to earthquakes. Pero, recently, you probably know this or experienced this better than me. 2012, Typhoon Pablo, December. Unfortunately, so nasa Japan pa ako niyan nung time na yun, yung thesis ko. Pina-finalize ko, tapos December 24 nga yung defense ko nun. Parang wala talaga akong napalitaan masyado, hindi yun nakapag-Facebook masyado nun. But, or anyway, mag-internet kasi busy. But yun, alam niyo yung storya. So maraming na-damage, maraming namatay, maraming natumba kahit mga puno. Well, sorry to show you this picture, but basically, that's the reality. And in fact, ang nangyari is, number 1, most or costliest typhoon, yung Typhoon Pablo. So more than $1 billion. I mean, ang hirap ma-imagine ng $1 billion. I mean, 1 billion peso pa lang pangalang. Anyway, and then, andyan rin yung Ondoy. Siguro narinig nyo rin yun. Kaming sa amin taga Maynila, kami naman naapektuhan naman kami niyan, pero makikita nyo Walang sinabi sa cost of damages due to Typhoon Pablo. Parang malayo sa kalahati. In terms of deadliest Philippine typhoons, actually noong 1991 nagkaroon ng isang typhoon. Nag-iiba-iba yung estimates pero at least 5,000 people yung namatay. Pero andyan yung si Sendong at si Pablo 2011-2012 nasa top 10. So yan mga nangyari recently. Yun nga, Typhoon Ondoy sa Manila. I mean, if you can just imagine, of course, sobrang daming tao sa Maynila, sobrang daming bahay, may tulay doon, yung traffic, tsaka yung tao nag-ipon doon dahil ang taas ng baha and so on. Yung mga bangka o barko, tinangay, etc. Mga kotse din, tapos ang daming kalat. So kakaiba eh. Kumbaga, I mean, minsan lang nangyayari din talaga ang mga ganyan. And then of course maraming nahirapan. Tumatawid na lang sila ng yung linya ng kuryente para lang makaiwas sa baha and so on. And just before that, yung 2006 Typhoon Milenyo, I don't know kung narinig nyo rin nun, pero ang storya naman yan, again, strong wind sa Metro Manila, ang daming billboard na nagtumbahan. So, of course, civil engineers, structural engineers nag-design ng billboards and anyway. So maraming, relatively, dapat walang matutumba, but anyway, may mga natumba. Mga nasa 40 yata out of, let's say, 1,000 or something. So, marami na yon. But may isang case na may natumbang billboard, natumba sa bus, na may mga pasahero, may namatay dun sa bus na yon and so on. Ito I think sa Laguna ito, so may mga natutumbang sign. Ito is, anyway, mga poste ng kuryente. At saka transformer. So maraming, ito natumba sa isang ang tawag niya sa Sasakyan. And then sa Makati, dahil maliliit yung mga, ang tawag doon, yung mga kalsada doon, parang nagkaroon ng funneling effect, may mga natumbang mga sasakyan. Then more of these, generally lightweight structures, nothing new. This one is just to let you know, 2004 Typhoon Undig naman sa Bicol region naman yung na-affect nito. Basically the same story, electrical posts, and then parang billboard structures, mga roof, mga under construction, pati mga tore natumba. So, kumbaga parang dahil nangyari ito recently, parang napansin ko rin, naging mas, which is good in a way. I mean, good. Of course, hindi magandang nangyari yung mga yun, but it's good dahil parang nagiging interesado yung mga engineers to learn about wind engineering din. So, I mean, andyan yung earthquake engineering, naranasan nga yung, let's say, 1990 earthquake and so on, marami pang ibang earthquake. Naging interesado sa earthquake. So ngayon, mas recently, mas nagiging interested sa wind engineering. Pero ayan, kung ipakita ko naman sa inyo yung total amount of damages, ito from 1901 to 2000 ito, walang sinabi yung earthquakes eh. So let's say $7 billion in damages compared to $500 million. Parang times 14, no? So basta sobrang daming napapatay na yung mga bagyo compared din ba sa earthquake. So of course, dahil mas maraming bagyo kumpara sa earthquake. But ibig sabihin, supposedly by design, walang damages or walang namamatay due to typhoons kung tama yung mga design. Of course, meron namang mga lumang structures din na hindi pa up-to-date sa standards. But ito just another update up to 2012. So kung sinama na natin yung let's say Pablo, Sendong, etc. Ayan, 4 times mas maraming napatay na ang mga typhoons, and then 18 times mas maraming damages yung typhoons in general total. So actually we have to put this in mind. Of course, earthquake engineering is very important, but you know, typhoon engineering too is very important, and people are recognizing that. So huwag na natin basahin yan. Sige, basahin na lang natin. Since the 1990 Luzon earthquake, summary part 1, many engineers have developed interest in earthquake engineering, but earthquakes in the Philippines on average certainly account for a large number of deaths and injuries and property damages. But in recent years, major typhoons have brought about plenty of, we could say, memorable damages. Kumbaga, hindi natin makakalimutan ng mga epekto sa buhay natin. No? Just to let you know, actually nag-umpisa rin yung wind engineering dahil dito sa bridge na to, Tacoma Narrows Bridge, hindi gumagana yung video pero kung isa-search nyo sa YouTube yan, makikita nyo kung gaano katindi yung pag-vibrate niyan. Basically, hindi nila akalain, mahina lang na wind, biglang mag-vibrate siya hanggang nasira na. So kung very interesting yan, pakisearch na lang sa YouTube, hindi gumagana yung video. I mean, dun kasi na gano'n again, it's gano'n no? Mukhang, kumbaga may nangyayari, so nagiging interesado tayong pag-aralan yan. So anyway, let's just start, before talking about site-specific hazard assessment in the context of wind loads, so let's talk about site-specific hazard assessment in the context of earthquake loads. If you're familiar with the NSCP, actually in a way, when you use the code, parang nagsa-site-specific ka na rin. Parang, kumbaga, of course, yan, the very first thing you have to do is establish what seismic zone, let's say you're designing a building or at a certain site, what seismic zone it belongs to, zone 2 or zone 4. And then you have to, kung zone 4 yan, you have to identify what is the seismic source type na i-consider mo. So A, B, or C, seismic source type. And then, after you identify that, you have to identify how far your building or site is from that seismic source. So, kung less than 5 kilometers ba yan, between 5 to 10, between 10 to 15, or more than 15 kilometers. Isang example na lang sa inyo, I don't know if you've heard, pero sa Metro Manila mismo, merong fault doon, yung valley fault system na tinatawag. So, you can imagine, yung maraming buildings ang less than 5 kilometers lang from that fault line. So, and then seismic source type A yun, zone 4. And then, after identifying the proper parameters, seismic zone, source type, and distance to source, if you know the site soil type, medyo specific to the site na yung makakalculate mong seismic load. Of course, well, that's one way of looking at it. In general, kumbaga kung titingnan mo itong mga combination na to, merong 65 different possible site-specific loads that you can generate. So, yeah, parang in a way, parang nagsa-site-specific ka na rin. Kumbaga nung unang panahon, wala pa itong mga to Parang zone lang. Pag zone 2, ito yung design seismic load mo. Pag zone 4, ito yung seismic load mo. Parang gano'n. So ngayon, medyo mas site-specific na yung ginagawa natin sa NSCP, sa latest versions ng NSCP. And then, you might be familiar with the Seismic Zone Map. So zone 4, zone 2, of course, Cagayan de Oro, Manila, basically almost all of the country except Palawan, Sulu, Tawi-Tawi, zone 4. And then may map din sa NSCP which shows the distribution of active faults, distribution of active faults, mostly source type A. Basically yung mga very strong, possibly very strong earthquakes yung ma-generate nila. Ngayon, yung NSCP natin, actually, or yung latest version, if you're familiar, NSCP 2010, ang balak sana doon is to pattern it. Kumbaga yung NSCP 2001, naka-pattern siya, naka-base siya sa UBC 1997, Uniform Building Code 1997. Yung 2010, ang original sanang intent doon, i-pattern na siya after yung International Building Code or yung mga ASCE or American Society of Civil Engineers na standard. Basically, ang naiba between IBC or ASCE, naiba dyan kumpara dun sa UBC is yun, parang pipiliin mo na lang yung tinatawag na SS and S1 values, spectral parameters, short period and one long period, 1 second. So anyway, just SS and S1. And then kukunin mo na lang yun from spectral acceleration maps. Once na-establish mo na yung SS and S1 parameter mo, kumbaga hanapin mo sa mapa yung site mo, so makukuha mo yung SS and S1 parameter, basta alam mo yung soil type, may site parang nag-site specific ka na rin. So ito yung isang example ng spectral acceleration map. Actually, this is for SS, for the United States of America. So mapapansin nyo, parang may mga contour lines dyan. Basically, kung saan medyo mas closely spaced yung contours, that's where there is very strong seismic activity. So you can see here, andito yung California, andito yung LA, San Francisco, ganyan. Andyan, basically highly seismic active area. So basta, let's say meron kang, may dinidesign kang building at a certain site, hahanapin mo lang dito sa mapa, makukuha mo na yung SS and S1 value, and then alamin mo lang yung soil type, kung SA, SD, SC, etc. And then parang may site-specific earthquake load ka na rin. Pero actually, when people say, so yung gamit na site-specific talaga na seismic load or seismic hazard assessment, yung para nga sa performance-based design. And ang ginagawa, I call it the true site-specific size. Kung gusto mo talagang gumawa ng site-specific hazard assessment, ito yung mga steps. In general, mga seismologists yung gumagawa nito. So determine fault type, distance orientation, you have to obtain ground motions similar to the faults and the events. You have to scale the ground motions. Basically, kailangan mag-match with your target, certain target peak acceleration and yung spectrum or frequencies. And then you do soil investigation, site characterization, site response, and very complicated stuff. But after you do this, or you ask someone to do it, so may makukuha na ng site-specific na seismic loading parameters. It could be in the form of time history, yung kumbaga parang nag-generate ka ng artificial earthquake, or pwedeng response spectrum yun, so pwede kang mag-response spectrum analysis. Pwede rin actually, makakuha ka na ng SS and S1 value. So, yun nga, kaya sinasabi ko, basta nagawa mo to, ginagamit natin kung makakagawa, kung meron tayo ng SS and S1 values, kung meron tayong spectral acceleration map katulad nito, para ka na rin nag-site-specific hazard assessment, more or less. And when it comes to response spectrum, I hope familiar na kayo sa response spectrum analysis. Actually, it's another term for it sa NSCP, I think, is linear dynamic analysis or something like that. Basically, if you have once you do site-specific hazard assessment, let's say yung site-specific response spectrum mo will look like this. So, medyo pangit tignan. Kaya ang ginagamit natin yung tinatawag na design response spectrum, ganito yung itsura, kamukha nung nakikita nyo sa NSCP. So, mas madaling gamitin for engineering purposes. Of course, mas exact kung gagamitin nyo to, but anyway, for engineering purposes, mas madali yung design response spectrum katulad ng nasa NSCP. And then yun na nga, once may response spectrum ka na, or time history, or SS and S1 value, simple na lang, papasok mo na lang yun sa equation, more or less, multiply by seismic weight, you get your seismic load. So, yun yung sa earthquake loads. Ngayon, pagdating sa wind loads, more or less similar din yung ginagawa. So, halimbawa sa latest NSCP, una, i-establish mo kung anong zone yung building site mo. Zone 1 ba? Zone 2? Zone 3? Of course, Cagayan de Oro, Misamis Oriental is in Zone 2. Alam niyo ba yan? No? Good. Tapos, zone pa lang yon. So, hindi doon nagtatapos. Kailangan alamin niyo kung may topographic feature na kailangan i-consider. Kumbaga, kung flat lang yung paligid for about siguro 1 kilometer around your building site, walang problema. So, no topographic feature. Pero kung medyo may mga bundok, mga hills, and basically different terrain. Well, not flat. Let's say nasa may mountain area ka, etc. So kailangan mo i-consider yun. And then you have to take a look at yung tinatawag na terrain category. Ano ba yung nasa paligid na nung building or site mo? Kung flat, kung open yan, kumbaga let's say walang mga ibang building, so open terrain yung tawag doon, category C. Kung may mga low-rise building na katabi, suburban terrain, category B. Actually, kung mga tall buildings, generally category A. Kung nasa tabing dagat, category D yung gagamitin. And then, ang mangyayari dito, dapat actually i-check mo bawat direction. So I'll show some examples here later, but so you're probably familiar with this NSCP wind zone map. Sa 2010 pinakita rin to. So and 150 kilometers per hour na sa zone 3 sa 2010. Pero yun na nga, so this is, the code-based zone map. More or less, parang basta sundin, ma-identify mo ng tama itong mga to, parang nag-site-specific wind hazard assessment ka na rin. Kumbaga, kung kukunin mo yung different numbers of combinations nito, at least 250 different site-specific wind loads yung makukuha mo. So, parang yun, parang nagsa-site-specific ka na nga rin. Pero yung merong, parang I'll just call it true site-specific wind hazard assessment, ganun din yung mga, parang may certain steps din, kamukha nung para sa seismic hazard assessment. Usually, kung sa seismic hazard assessment, kailangan ng seismologist, dito, hindi kaya ng, well, I don't know, wala pa akong, well, anyway, it's in the field of meteorology na basically, and more specifically, I'll call it engineering meteorology. Usually, yung mga meteorologists, they do measurements and so on, weather forecasting, pero hindi yung, not much of yung, ang kailangan gawin kasi dito is yung tinatawag na extreme value analysis. So kasi we have to define risk and so on. Kasi that's what we're designing for. Parang there's a risk that may 200 km per hour winds that we will experience. So how do we design for that? So that's what we're interested in. So of course, similar steps as for earthquake. First, we establish the storm type. So typhoons ba lahat? Kasi let's say we have thunderstorms din. So it's another type of storm. It also has strong wind. Ayun ba yung dominant storm type? So you have to check both actually. Lalo na sa, let's say sa Mindanao. Kasi closer to the equator, less, if you notice, mas malakas yung, ang tawag dito, winds dito. Basically, closer to the equator, mas humihina yung wind. Typhoon wind. And then yung thunderstorms medyo nag-govern. And then you will obtain annual maximum wind speed records, at least from nearby stations. You need to apply data corrections for topography, terrain, and height, etc. And then you fit to an extreme, yung basically parang probability distribution, mag-fit ka, and then obtain wind speed at whatever annual probability you're interested in. So usually sa NSCP, yung basic wind speed natin is 1 in 50 year annual probability. So 1 in 50 annual probability. So 50-year return period. So after you do all this, you get your actually site-specific basic wind speed pa lang. So actually, when we say site-specific sa wind hazard assessment, sa wind speed lang natin, sa basic wind speed V lang natin, yung nakukuha natin site-specific talaga. And just to mention, may 56, let's say may 56 stations yung Pag-asa where they do wind measurements. 50 of those stations have data from 1961. So actually yun yung ginamit for the NSCP. And then ang required natin is 50-year return period wind speeds at 10-meter height. in flat open country terrain. So basically, basta may basic wind speed ka, so it could be from the NSCP zone map or from yung, ang sabi sa NSCP, regional climatic data. But basically, it means site-specific basic wind speed or parang nag-site-specific analysis ka. Pero hindi pa talaga yun site-specific eh. Pumapasok pa dyan yung ibang factors yung sa terrain, topography, direction, and then dun pa lang talaga magiging site wind speed. Specific to your site, yung wind speed mo. Ibig sabihin, kahit na nag-site specific analysis ka nga dito para makuha mo yung basic wind speed, pero kung hindi mo naman nakuha ng tama to, hindi pa rin yun yung tamang site wind speed talaga. So, very important to take care of that. And then finally, you take site wind speed, multiply it by yung importance factor, that's the design wind speed. So, more often than not, let's say zone 2, let's say Cagayan de Oro, zone 2, 200 kilometers per hour. Ito pa lang yun eh. Basic wind speed pa lang yun. Pero, pag may dumating, let's say, na bagyo, hindi dapat dun kino-compare actually. Dapat sa site wind speed and even sa design wind speed. But anyway, discuss natin yun. Ngayon, of course, when we talk about wind speed, so when it comes to terrain, so let's say exposure C open, exposure B, may mga konting trees or low-rise buildings, exposure A kung may mga high-rise building. Basically, ang nangyayari dito, mas matataas yung wind speed if you're in a more open terrain environment. So here you have a lot of obstruction, so the wind speeds are generally lower. It's due to basically parang if you can just imagine this as parang surface roughness. So on the surface of the earth, you have some roughness elements. If you're in exposure A, it's the roughest parang surface terrain, and that's why nagkakaroon nagiging less. Kumbaga, tumataas yung friction on the wind, and therefore kaya bumababa, mas mahina yung wind sa exposure A, for example. This is just one example photo actually galing to sa ASCE 7 standard. Just to let you, siguro, I'll just discuss it na lang. Let's say you're designing this building, ano yung exposure category niya? Anong palagay niyo yung exposure category niya dapat? B? Hindi ba B ba? O A? High-rise yata ito eh. Trick question yun. So, yun yung gusto ko i-emphasize eh. If you're designing, let's say, a certain building, you have to look at each direction. So if you're considering the wind coming from this direction, papunta dun sa building na yun, you might use exposure A, for example. If you're considering wind coming from this direction, generally walang obstructions, you need to use exposure C. Wind coming from that direction or from this direction, may mga low-rise buildings, may mga puno, maybe you should use exposure B. So yun yung, one of the things I wanted to emphasize. You have to look at each direction. I mean, to be, kung gusto mo talagang specific yung to the site, yung, let's say, wind speeds mo. So it's actually, each direction may specific terrain exposure ka, and therefore specific wind speeds. Of course, you can just assume exposure C na lang palagi, basta hindi katabi ng tubig. Conservative naman masyado, so hindi rin maganda. Another example is this one. So, of course, let's say you're designing this facility. If you're considering wind galing dito, dapat exposure D. So short, kumbaga adjacent to water. Pero if you're considering wind galing dito, dapat exposure C siguro, kung wala namang obstruction. So of course, again, each direction pwedeng mag-iba yung exposure category. again, you can be conservative and sabihin mo na, i-assume mo na lang exposure D, pero again, that's not, doing your job very well kasi dapat i-balance natin yung economy and safety, di ba, as designers. And then topographic factor. So if you have used NSCP 1992 or earlier, wala pa to, yung tinatawag na topographic factor. Basically, kung meron kang let's say, escarpment na tinatawag or parang, kumbaga galing dito parang may bangin pa ganun, pero kung kinoconsider mo yung wind galing sa bangin, bumibilis yung speed, nagsi-speed up yung wind as it goes up that slope. Ganun din if you have a ridge or hill. So, actually meron na akong alam na isang structure on top of a hill siya, designed according to NSCP 1992, bumagsak. And I think it's because of, because NSCP 1992 and earlier didn't yet consider itong topographic factor. So very important to consider kung hindi flat yung topography around your site. And anyway, may mga kilala akong gumagamit pa rin ng NSCP 1992. Well, legally, hindi na yun, di ba? Hindi na dapat ginagamit. Just quickly, actually, to give you a background, yung wind zoning natin nagsimula nung siguro noong 1973 study ng isang Amerikano si Sinyu. So doon nagsimula yung Zone 1, Zone 2, Zone 3, and parang ang nangyari, pero 16 stations lang actually in-analyze niya, pero doon nang galing yung sinuperpose ko. More or less yung zoning natin na nakita sa NSCP from 1977 to 1992, doon nag-base. Pero again, may problema rin with let's say NSCP 1992, may mga kilala pa rin akong gumagamit niyan. Essentially, if you use NSCP 1992, there's possible under-design of about 25% in Zone 1 kung ginagamit pa rin yung NSCP 1992. Sa Zone 3, medyo safe actually mga structures, parang may over-design doon. Sa Zone 2, medyo in terms of the wind speed, wala masyadong difference. So sa Zone 1 lang actually problema kung ginagamit pa rin yung NSCP 1992 in terms of the wind speeds dahil may under-design. And then you're familiar with this, I showed you this earlier, yung current wind zone maps natin. Just to let you know, noong 2005, si Dr. Garciano, professor siya ngayon sa Lasal sa Manila, nag-aral siya din sa Japan, and then 2005, may study siyang ginawa, present niya to sa isang ASEP convention. Basically parang a little bit of an improvement over our 3 zones. So parang pinopropose niya, parang hybrid na zone and contour map. Basically, this can be used as well, but of course, it's not official. But it has a rational basis. So, and just to let you know, yung Pag-asa may ginawa sila. Kinuha nila yung mga maximum per station. Tapos nagguhit-guhit sila to come up with this contour map. May gamit to, ang problema dito, hindi natin to pwedeng gamitin sa for engineering. Kasi this just yung record ng mga maximum wind speeds na na-experience around the Philippines. So, pero ang kailangan natin for design is yung let's say yung tinatawag natin mga 50-year return period wind speed and so on. Although yun makikita nyo nagpa-match ng konti dito, 250, 200, 185 generally around zone 2, 100 kilometers per hour lang dito until year 2000 to. But so medyo may match naman ng konti sa 50-year wind speeds natin. Just to let you know then, ito yung pinopropose sana originally for NSCP 2010. Pero anyway, ginawa na lang namin mas madali, table form na lang yung ginawa sa NSCP 2010. And then ano na per province basically. So para mas madaling gamitin, hindi katulad nung let's say dito, actually hindi mo nga, aalamin mo pa kung nandun ka banda, paano na, zone 2 ba o zone 3 yung gagamitin, so on. So medyo mas madali nang gamitin yung NSCP ngayon. So, ang isang point ko rin gusto sabihin, kahit na may parang tinatawag na site-specific analysis ka to arrive at the basic wind speed, so kailangan mo i-identify nga yung terrain, topography, per direction, para makuha mo yung actual na site wind speed for your building or site. And then, marami pang ibang parameters actually. So even if you got that right, pero if you don't get these other things right, yung tinatawag na gust effect factor, tsaka yung mga aerodynamic coefficients, magkakapaliwala yung site-specific analysis mo. Unlike, basically sa seismic load, nag-site-specific analysis ka, yun na yun, yung gagamitin mong load. Dito, kahit nag-site-specific analysis ka, tapos, yun na nga, mali naman yung pag-calculate mo ng gust effect factor, o mali yung ginamit mo na gust effect factor or force coefficient, so, baliwala. So, important din yun sa wind. Yun yung isang difference between earthquake, let's say earthquake, sa earthquake context and sa wind context. So, yung gust effect factor is basically yung sa dynamic response na tinatawag. It's also called dynamic response factor in other codes. Let's say sa Australia, yun yung terminology nila dyan. It's actually a function of site wind speed, structure size, and the structure's dynamic properties, yung natural frequency and damping na tinatawag. Sa NSCP, meron tayong mga formulas for that. So you can also see, basically, kung nagbago yung site wind speed mo din, naapektuhan rin yung gust effect factor mo. If you're talking about a large structure or a small structure, between the two, naaapektuhan yung gust effect factor. And if you've used the code before to design, maybe you assume gust effect factor equal to 0.85. So sabi kasi sa NSCP for rigid structures or for rigid buildings. The truth is, yung 0.85 na yan, it is nasa galing sa American code. Ang intention dyan sa 0.85 para gamitin yan for low to medium-rise buildings in the USA. Yun yung tinatawag na rigid buildings. So in short, kung yung building na dinedesign mo ay hindi low-rise or medium-rise at wala sa USA, technically dapat hindi 0.85 yung gagamitin mong value. Okay? So, technically you have to calculate, basically in the Philippines, just calculate it. And hindi naman masyadong mahirap, nandyan sa NSCP na lahat ng formula. Mukhang komplikado yung formula, parang ang daming kung anong simbolo. Pero ang katotohanan is, ma-program mo lang to sa Excel, and then simple na, plug and play na lang, and so on. So pwede mo itong gamitin for any type of structure, whether flexible building na tinatawag or dynamically sensitive, yung mga tall buildings, pwede mo rin gamitin to for low-rise buildings, technically. In fact, pwede rin siya for billboards, etc. But meron tayong separate na formula for billboard structures and for truss towers. Basically, nanggaling to sa formula na nasa US din. Well, dinevelop rin sa isang American standard. So, general formula lang siya. In-adapt natin for yung NSCP. Pati for cables. So if you're designing transmission tower, you can also use this. So it came from ASE Manual of Practice number 74 actually. And then, like I said, to calculate itong gust effect factor, you need to have a good estimate as well of yung dynamic properties ng building. So, most importantly, yung tinatawag na natural frequency, tsaka yung damping. Yung natural frequency sa earthquake, where usually ang pinag-usapan natural period. So, halimbawa, if you have a 10-story building, yung natural period niyan siguro, yung natural period of vibration, 1 second. Yung natural frequency is just the reciprocal of natural period. So, yung 1 second magiging 1 hertz. Yung 2 seconds na natural period magiging 0.5 hertz. and so on. So, but anyway, may mga formulas dito for concrete building, steel building, kung allowable stress design yung gagamitin mo, o kung ultimate strength design or LRFT, for billboard structures, truss towers, meron na rin dyan, etc. And then, ang ginawang style dito is pasimple ng, kumbaga kung gusto mong gamitin yung mas simpleng formula, medyo magiging mas conservative ng konti yung makukuha mong, let's say, gust effect factor or wind loads. But andyan yung medyo mas detailed na formula. This is based on actual measurements. So may mga measurements, let's say from around, from different places actually from, na similar characteristics dito sa Pilipinas. So anyway, kumbaga based din naman sa actual yan. And then sinasabi rin dito, you can also use, of course, lalo na for natural frequency, you can also use yung computer simulation. So sa STAAD or sa ETABS, you can calculate natural period. Pag na-calculate mo na yung natural period, inverse lang, or reciprocal to get natural frequency. And then of course, and then damping ratio, dito may mga suggestions rin dyan. If you want to be simple, just use 1% or 0.01 for steel, 1.5% for concrete, or so simple lang. Pero if you want to be a little bit more detailed, so andyan yung medyo mas detailed na computations, etc. Pero very simple formulas lang din yan. So you need all of this to itong natural frequency and damping estimates to calculate gust effect factor. So yun yung gust effect factor to account for dynamic response. Again, so you have to get that right. You have to get the aerodynamic coefficients right as well. They are all in the NSCP for certain shapes. So let's say if you have a flat roof, gable roof, dos aguas yung tawag natin dyan, hip roof or quattro aguas mo yung tawag dyan. Ang problema, hindi naman lahat ng building ganyan yung shape. Diba katulad nito I think sa Naga din to sa Bicol, parang dito, dos aguas siya, gable roof, pero parang meron pa siyang ibang portions ng roof. So, paano na yun kapag iba yung shape ng building mo kaysa nandun sa NSCP? May tatlong sagot. Una is, pwede kang gumawa ng assumption. Pwede kang i-assume na itong portion na to, siguro gagamitin mo gable roof. Gable roof. And then, itong portion na to sa baba, siguro, or dito, gagamitin mo hip roof. Parang gano'n. So, pwede kang gumawa ng assumptions based on yung nandun sa, kung ano yung nandun sa NCP. Ang second option is, kukumbinsin mo yung architect, sabi mo, palitan mo yun. Pero good luck na lang, syempre. Sabihin mo, wala sa NCP yan eh. Pero good luck na lang. Pang-apat is actually, pangatlong way para makuha mong yung tamang force coefficients or aerodynamic pressure coefficients for a different shape of building or roof na wala sa NCP is actually wind tunnel test. Ngayon, mahal magpa-wind tunnel test. Let's just say ang rinig ko nasa 1 million to 1.5 million. Siguro 1 million na lang. Magkano ba let's say ito, mga magkano ba ito? Parang ang mahal masyado. So kaya actually option lang yun siguro for tall buildings. So best bet mo, yun na nga, gagawa ka na lang ng assumptions kung hindi mo kaya i-convince yung architect. Of course, meron din ibang roof dyan, ibang types of shapes, monoslope roof, mansard roof, step roof, nawala yung biglang nagka-problema din sa. But anyway, may dome roof, meron ding mga multi-span roof. And then yun, mapapansin nyo, basically, depending on the location around the building, nag-iiba-iba rin yung pressure. So actually, sinimplify na nga sa code. Ang totoo is, hindi naman uniform distribution ng ang wind load. So sinimplify na lang na uniform distribution halimbawa mula dito hanggang doon, ganun kalaki yung wind pressure, mula dito hanggang doon, ganun kalaki yung wind pressure, and so on. So basta important to consider lang at different locations, nag-iiba-iba yung wind pressure.